Okay, welcome back again. What we're going to do now is we are going to continue on in the grand scheme using exponents, but now we're going to look at exponentials. And you're maybe not sure what the distinction is, but I'm here to tell you. So we're going to look at exponentials and their graphs. Right? So that's what we're going to look at. We're going to look at exponentials and their graphs. Now, we've been doing exponents, and we know what an exponent is, so we're good there. But what we're going to find here is we're going to look at something else. So I'm going to start by simply writing the base exponential that we are going to be responsible for in the grand scheme in this course. Certainly, we go much more advanced than this if you were to try and take advanced functions next year, but you're not. And so we're going to just look at some of the basics. So we're going to start by looking at the very most basic, and we're going to look at y equals some number, and I'm just going to call it a to the exponent x. Now, this a is a number, so where a is a positive, and that's important that it's positive, constant number. Okay, so y equals a to the exponent x. We're going to do more than this, but this is where we're going to start from. So let's look at, as an example, we're going to look at y equals 2 to the exponent x. How does this differ? Well, this is different because the variable is in the exponent, right? We have never done that, right? If you think about other stuff we've done, we have done y equals x squared. They're similar. They both have an exponent, and they both have a base, and they both have an x, and they both have a 2. But over here, the variable is in the base, and the exponent is a number. Over here, we have the number is the base, and the variable is the exponent. And that has a huge difference. So this right here, well, that is an exponential. This one, if you recall, of course, hopefully you remember what that one's called. That was, because we spent a lot of time on it, that's a quadratic, okay? Or a second degree function, right? Lovely. Okay, so now, all right, we're going to graph this thing. And you probably, why would you have any idea? You should have no idea. If you think back to grade 9, depending on who you had in grade 9, when we first started to graph stuff, what did we graph first? Well, we graphed the equation of a line. So we graphed y equals mx plus b. And depending on who your teacher was, maybe the very first thing that you did when you're graphing y equals mx plus b was to graph it using a table of values, right? And that's what we're going to do again. We're going to do another table of values here. So here is the table of values that we're going to fill out. So I'm going to say, here's my table of values. It's going to be x in this column. Oh, that's a terrible line. Oh my goodness. Let's actually get my shift going on here because I'm going to do some graphing. Lovely. There we go. So there's my x column. We're going to have a y column. We're going to leave ourselves some room. We're going to do some calculations. And then over here, we are going to write our ordered pair that this generates, right? So this is going to be x comma y. And this set of ordered pairs is what we're going to use to graph and see what this thing looks like. So here are the values that we are going to use for x, and we're going to substitute into here. We're going to do -3 and then -2 all the way up to +3. That's what we're going to do. I don't want to write them all in. I don't want you to write them all in yet because we're going to need to probably do some work. So I want to leave some room. So here's how we're doing it. We're going to do y equals 2 to the exponent x. Well, our x values, these x values subsequently are going to get substituted into here. Okay, so first one is going to be y equals 2 to the exponent -3. Now, you could just go ahead, if you're a slacker, and grab your calculator and type that in. And that'd work. But I want to revisit some of the stuff that we worked with yesterday. This negative is going to cause me to reciprocate the base. Well, the base is 2. So to reciprocate it, I've got to put it as 2 over 1. When I reciprocate that, that's going to be 1/2. And that gets rid of the negative. And then, and I'm doing this in more detail than we would normally do. I know this is to the exponent 1, and this is to the exponent 1. So this is going to become 1 cubed over 2 cubed. Well, 1 times 1 times 1 is just 1. And 2 times 2 times 2, it's not just 2, it is 8. So this evaluates to the 1/8, which is 0.125. So had you just taken 2 to the exponent -3 and typed that into your calculator, you would get 0.125, which is all good, okay? So I'm going to write this as an ordered pair. The ordered pair is -3, there's the x value, and 1/8, or 0.125, okay? Going to do the exact same thing for -2. Maybe you could pause the video and do -2, -1, 0, 1, and 2, and get all of your ordered pairs. That would be a good exercise. Go, go, go. So I'm going to go ahead and I'm going to do it. So we're going to have y equals 2 to the -2, which is going to become 1 over 2. And I'm going to multiply in my exponent right away. So that's going to be squared and squared, which just becomes, well, 1 squared is 1, and 2 squared is 4. So my ordered pair here is going to be -3, 1/4. Okay. Oh, sorry, -2. Goodness gracious. -2, 1/4. On we go. Y equals 2 to the -1. Well, that's going to flip it over. So it's going to be 1/2 to the -1, or 1/2, excuse me, to the 1. So this is just that, well, anything to the 1 is just itself. So it's going to be 1/2. So it's going to become -1, 1/2. Lovely. Keep this going. So we're going to have y equals 2 to the exponent 0. Well, hopefully you remember anything to the exponent 0, with that one weird case exception, is 1. So this ordered pair is 0, 1. On we go. Right, here we are. Then we're going to do y equals 2 to the exponent 1. Well, that's just 2. So that's going to be 1, 2. And then we're going to have y equals 2 to the exponent 2. Well, 2 squared is 4. So this is going to be 2, 4. And then we're going to have y equals 2 cubed. And we're going to get 8. And you're going to see here that we're going to get 3, 8. Now, this is why it's kind of nice to do those fractions. Look at these are just the reciprocals of these, and that's always going to be true. The negative version is just going to be the reciprocal of the positive version, okay? So there's a whole series of ordered pairs. So I'm going to, well, I don't have a graph, I was just going to say I'm going to drag a graph in here, but I don't have a handy graph paper in here, so I'll just do it here. I'm going to go ahead and I'm going to graph this. Now notice, I'm only going to bother with quadrants 1 and 2 because quadrants 3 and 4, I don't have any negative y values, so they don't go down there. So this first point, negative, so maybe I'll label these off a little bit. So there's -1, there's -2, there's -3, and then we got 1, 2, 3, and then up here we've got 1, 2, I'm going to run out of space, oh well, 3, 4, and then in theory it goes down here, and we got -1. All right, so first ordered pair, -3 and 1/8. So there's -3 and 1. Actually, let me grab a different color, whatever color that is. -3 and 1/8. So that's just barely above the x-axis. And then -2 and 1/4. Well, it's not much higher, but it is a bit higher, so like up to there. And then -1 and 1/2. Well, 1/2 is in this vicinity right here. And then 1 is up here, and then 1 and 2 is right there, and then 2 and 4 is right there, and then 3 and 8 would be somewhere way the heck and gone, I don't know, up in that vicinity. And so if, now this is going to be really challenging for me to do on this tablet, but I will do my best. We're going to try and smoothly, no, that's not smoothly at all. You can do it better on your paper. It's hard to do on a tablet. We're going to try and smoothly connect this and see what this graph looks like. Okay. And there it is. Now, what's interesting about this graph, okay, is the further out this direction we go, the lower it gets. But here's the key. It can keep getting lower, but it can never actually reach the x-axis. It'll get close. So if you were to do like -10, you'd do, all right, well, it's 2 to the exponent -10. If you typed it in your calculator, it would be a decimal, be a really small decimal. It'd be like 0.0000000 and like 1. And it will always be a positive number, but it will get closer and closer and closer to the axis. So this just keeps getting closer and closer and closer and closer and closer. Well, didn't there, but closer and closer and closer and closer to the axis, but never actually touch it and never go below it. Okay. And so that concept of getting closer and closer and closer and closer and closer, but never touching it, has a really special mathematical name. And as it gets close like that, when the function gets closer and closer, function gets closer and closer to the axis, it is called an asymptote. Okay, I'm going to write that bigger because that's an important word. So that is an asymptote, and I'm over pronouncing it. It's asymptote. I want you to notice that last consonant right there is a T and not a P. A huge number of people, even people who should know way better, say asymptote, but it is not. It is asymptote. Okay, so that's really important. So an asymptote is when you get really, really, really close to something, but you don't ever actually reach it. It would be akin or similar to if you ask someone to stand up and go halfway to the door, and then ask them to go halfway to the door again. And you say you can go halfway to the door as many times as you want. Well, if you only go halfway to the door every time, you will never get there, right? You can go halfway again. There's not any limit to the number of times you can go halfway to the door, but you will never get there if we're only going to go halfway. And so an asymptote is just like that. You can get half closer and then half closer and then half closer and then half closer, but you never actually get there if you're only going halfway every time. So that is called being an asymptotic, but that is an asymptote. And every exponential equation that we're going to play with, so when the exponent is a variable, is going to have an asymptote in it. Now, the asymptote for this particular one is the x-axis. So the asymptote's equation, and I know I'm pouring a lot of things on you right now all at once, but the asymptote here is the x-axis. And the equation of the x-axis, if you remember grade 9, is y equals 0, right? Because it's really 0x plus 0. Well, a slope of 0 means horizontal, and a y-intercept of 0 means at the y, or at the origin. So the equation of this is y equals 0. And that's important. We're going to, spend some time on that. So here's what that looks like. So in the grand scheme, right? So I'm just going to kind of, some features that are really important and worth noting is that it has a y-intercept of 1, right, where it goes through the y-axis is at 1. We got it right there. And that it is asymptotic to the x-axis. So it goes down, keeps getting close, and doesn't actually touch it. So I'm going to get rid of that one because that was a poor job. It gets closer and closer and closer and closer. My hand is sticky. And it's getting like that, okay? And then on this side, it grows wicked fast. It just books up like that, right? If so for an x value of 3, it was at 8. At an x value of 4, it's 16. And an x value of 5, it's 32. And then 64, and then 128, and then 256, and then 512, right? It gets big fast, way faster than a parabola, way faster, okay? Exponential equations go fast. So, when you're watching those horror movies, it's like, oh, it's growing exponentially. That means it's growing wicked fast, right? So there you go. So that is the general shape of this particular function, okay? So the general form that we start with is y equals a to the x. We've done it with the base value of 2. How say we do it now with a base value of, let's say, 1/3? So we're going to do the exact same exercise. So I'm going to give you the equation y equals 1/3 x, 1/3 to the exponent x, excuse me. And I would like you to graph, again, using a table of values. So I want you to do the same exercise. I want you to still have x values of -3, -2, -1, 0, 1, 2, 3. And I still want you to do y equals 1/3 to the exponent x. And then over here, I want you to write all of your ordered pairs, x, comma, y. And then when you're done, I'm going to get you to, of course, graph them as well. Okay, so we're going to graph those as well. Okay, so I would like you to go ahead, pause the video. It's a good exercise for you to try on your own. Generate all of your ordered pairs and then plot them. Unpause it, come back and see whether you've matched me. Welcome back. All right, here we go. So I'm going to show a lot of details in the first couple, and then I'm going to just make it a little bit more speedy. So we're going to have y equals 1/3 to the -3. Well, the negative is going to cause this to flip. So this becomes 3/1 to the +3. Well, any number divided by 1 is just itself. So this is really just 3 cubed. 3 times 3 times 3 is not 9, it is 27. So this is going to be the ordered pair, -3 and 27. Next one, y equals 1/3 to the -2. Negative is going to cause it to flip. 3/1 is just 3. So it becomes 3 squared. 3 squared is, of course, 9. So this is -2 and 9. Y equals 1/3 to the -1. I'm going to flip it. It's going to become 3. 3 to the exponent 1 is, well, it's 3. So this is -1 and 3. And then we're going to get here and we're going to say, all right, y equals 1/3 to the exponent 0. Hope you remember anything to the exponent 0 is 1. So it is 0 and it is 1. Okay, lovely. And then we have y equals 1/3 to the exponent 1. Anything to the exponent 1 is just itself. So that's 1/3. This becomes 1, 1/3. Y equals 1/3 squared. Well, 1 squared is 1. 3 squared is 9. So it's 1/9. So it is 2 and 1/9. And then y equals 1/3 cubed. Well, it's really exponents of 1 on those. So it's, it is 1 to the exponent 3 over 3 to the exponent 3. 1 to the anything is just 1. 3 cubed is still not 9. It is 27. So this becomes 3 and 1/27. Again, I'd like you to notice the symmetry. 27, 1/27. 9, 1/9. 3, 1/3. And then just 1. Okay, I'm going to go over here and plot these points. So -3 and 27, way up here, right? So -3 and 27, there's that point. And then -2 and 9, so much lower, but still high. So -2 and 9. And then -1 and 3. There it is, so -1 and 3. And then 0 and 1. All right, so it goes through at 1, just like it did in the last one. Interesting. And then 1 and 1/3, so it's not up very high. And then 2 and 1/9, so it's really low. And 3 and 1/27 is like, practically indistinguishable from the axis, but still above the axis. So now I'm going to again try and do my darndest to keep it, relatively smooth, but it's hard to do. Here we go. And then it keeps getting closer and closer to the axis, but in theory does not ever touch it, even though I'm touching it like crazy. It's just hard for me to do. Okay, there you go. So now notice this one got bigger the further it went to the right. This one gets smaller the further it gets to the right. Thing is, though, it is still asymptotic because it's still getting close to this axis, right? The further out it goes, the closer it gets. Now it gets closer to it on the right instead of on the left like the last one did, but it's still that. So it's still the x-axis is getting close to, and the equation of that is y equals 0. And also worth observing that the y-intercept is still equal to 1. Okay, what we have explored here are two different types of exponential equations. The first that we explored is called exponential growth. And the second one that we explored is called exponential decay. And we're going to kind of debrief about these things. So, exponential growth occurs under the following circumstances. So, the general form, to begin with, we're going to get a little bit more sophisticated, but for now, the general form is y equals a to the exponent x, where again, a is a constant. But for exponential growth, here's what we're going to look for. Any a value that is bigger than 1, any a value bigger than 1. So a, for exponential growth, a must be greater than 1. So that is a greater than 1. So any number a could be, if it's greater than 1, we are going to have exponential growth. So it could be y equals 1.1 to the exponent x. That would count. It could be y equals 7 to the exponent x. It could be y equals 12.4 to the exponent x. Those are all examples of exponential growth because the a value is constant and a is greater than 1. Now, what's special about that? Here's what's special about that. All exponential growth equations basically look the same. Okay? They're all going to get bigger the further to the right we go. And I'm kind of lying here. If they're of this form, they're always going to have a y-intercept of 1. So it's got a y-intercept of 1 for now. And they are going to get bigger, right? So they're always going to look like this. It doesn't matter, well, not with that hump there, but you get the idea. This is what all exponential growth equations are going to look like. All of them. 1.1, 12.4, 72. In the grand scheme, they get close to the y-axis or the x-axis the further out this direction we go, and they book off to infinity really quickly on the right-hand side. Exponential decay. Okay, so exponential decay, y equals, it looks the exact same, a to the x. Again, a has to be a constant, but this time a must be less than 1, but it's got to be positive. So 0 is the small end of a, so you can't use 0. It's got to be positive. So a has to be between 0 and 1. So I'm going to write that. So a must be between 0 and 1. Okay, so some examples. Y equals 0.1 to the exponent x. Y equals 3/4 to the exponent x. Y equals 0.9 to the exponent x. All of those things have an a value between 0 and 1. And those are called exponential decay. Okay, so what they look like in the grand scheme, you probably got a good idea because we did one up there, is as follows. They're also, interestingly, all going to have a y-intercept of 1. So they've got I'm going to write that higher. Go right over here maybe. A y-intercept of 1. Now, again, that's for this case. There are going to be weird ones. But this time, instead of it getting big on the right and small on the left, it is backwards. In fact, it's exactly backwards. So it books off to infinity over here, right? So it gets big over here. And then on this side, it comes down, zooming on in to the axis over here. Okay, so this is growth, and this, well, this is decay. Now, these seem pretty obscure. Interestingly, particularly for growth, this is really, really, really prominent in the real world. Okay, financial math is all about exponential growth. Sadly, in the times that we have right now, the whole flattening of the curve thing that we've talked about with COVID and coronavirus, that I'm sure that you couldn't avoid it on the news, was about exponential growth as well. I'm not going to dwell on that, but suffice it to say, exponential growth is very, very, very positive, and shows up all over the place in the real world. Exponential decay is less prominent. Where you may have heard of this. So if you've watched a disaster movie or played a video game, radioactive half-life. I'm sure you've probably heard of Half-Life. There's a game called Half-Life. Half-life is an exponential decay equation. And so exponential decay is as something gets smaller, but at a constant proportion. That is going to be exponential decay. Okay, so lovely. On we go. So yeah, this is good. So for now, actually, I think I'm going to stop there. I'm going to get you to graph each of the following for your homework questions to practice on. So what I would like you to do is I would like you to graph using a table of values. So the exact same process we just had here, using a table of values. And again, table of values is always going to have, unless I say otherwise, -3, -2, -1, 0, 1, 2, 3. Okay, each of the following. So I would like you to graph y equals 4 to the exponent x, and I would like you to graph y equals 1/4 to the exponent x. So you can practice those two, graph them. And what I'd like you to do is I would like you to graph both. Oh, that's a nice one of those. I would like you to graph both on the same set of axes. Okay, so that's what I'd like you to do. Graph them on the same set of axes. Okay, thanks, guys.